Hello everyone, my name is Samuel Bradford from Solar Gators, and this is going to be another video about the power section of our Solar Gators PCBs. So where we left off last video was we created this buck converter circuitry. So the center here is our buck converter. We have some input circuitry, so a main filtering capacitor, a resistor choosing the mode slash S configuration, a output inductor and capacitor for filtering, the switch output, a 100 kilo ohm pull-up resistor for the power good pin, and a 249 kilo ohm resistor for the power reset pin. Okay, so this is most of it, but there's a little bit of extra stuff that we have to add for our solar gator circuitry. Um, and the first thing we're going to focus on is our reverse polarity protection. So the main voltage supply for these boards is going to be the 12 volts coming from the going to be the 12 volts coming from the power board, and we want to be able to protect the board from somebody, say, accidentally plugging something in backwards. And for that, we use reverse polarity protection. To achieve this reverse polarity protection, we use a P-channel or a P-channel FET. So this one is the A04407A, and I'm going to go ahead and connect it up. So we're going to connect this right pin to power V in, the bottom pin down to ground, and I'm going to route out this pin and call it, and place a net label calling it plus 12 volts input. Now, I want to describe a little bit to you on how this works. Okay, so first we're going to go ahead with the example of the everything being plugged in correctly. In that case, you have a 12 volts potential here and a ground potential here, 0 volts. So that means that there is, and also you can see that there's a small diode across this P-channel MOSFET, which indicates around a 1 volts-ish drop across from here to here. Okay, so that means you're going to have 12 volts here, 11 volts here, and 0 volts here. This P-channel MOSFET is going to close and reduce sort of that, and basically tie these 2 points together if there is a voltage difference greater, or I'm sorry, if there is a voltage difference of some value between these 2 points. In this case, I believe it's anything greater than 4 volts. And in this case, because of this 1 volt drop, you have 12 volts here, 11 volts here, and 0 volts here, meaning there's an 11 volt difference across these 2 points, meaning that this is going to close, reducing the difference between these 2 points from this 1 volt drop to a very small drop that can be represented using the RDS on value that you can find in the data sheet for this part, but it's going to be very small. And so that is the sort of correct way to plug it in. If somebody, for example, plugged it in backwards, you would have something a little different. In that case, you would have ground here again, but you would have negative 12 volts here. You would have your 1 volt drop here, bringing this down to negative 11 volts, and this would still be 0, meaning your voltage difference across here is now 11 volts, or sorry, is now a negative 11 volts, meaning this is obviously staying open. But you might ask, well, you still have negative 11 volts here. But in reality, you don't, because this is a diode. And this is going to be negative 11 volts here and negative 12 volts here, which means that the potential here is less than the potential here, meaning that this diode will not turn on, and you will have no current flow between these 2 points, achieving your reverse polarity protection. Now, that is good for our reverse polarity protection, but on solar gators, we like to sometimes power our boards from USB ports. These USB ports commonly operate on 5 volts, and we use these for, whenever a board's not in the car, for testing it and programming it, maybe even uploading the configuration values to a board. So we're going to go ahead and use this diode. I'm going to explain how everything works in a moment. First, we're going to route it up. So we're going to have this, and we're going to connect it after our reverse polarity protection because it's pretty hard to plug in a micro USB cable backwards. My dad did it to one of my speakers, and yeah, let's just say it broke. Okay, so route that and add a net label, PN. I'm going to call this USB underscore VN. Okay, so let's talk about how this works. You have your, assuming let's go through the different cases. If you have just your 12 volts, the easiest ones are obviously just your USB voltage is applied, and it runs through your diode and powers the rest of the board. You have, in the other case, you just have 12 volts input, and that powers the rest of the board. This would be 0 volts, and this would be 12 volts, which means no current is going to go this way through the resistor because the potential on this side is lower. Now, the most interesting case comes when you have both things plugged in, right? You might have this plugged into your computer, this plugged into the car. And you want to make sure you don't damage your computer or damage the rest of the car. So in this case, you have 12 volts coming in here, right? This whole thing is going to probably be drawn up to 12 volts. And this is going to be at 5 volts, meaning that this has a higher potential than this side, and no current is going to flow, protecting your USB device. And there you go, that's basically how this works. One point to note is if you know anything about diodes, you're probably yelling at me right now saying, why would you use a diode? That's going to be a very inefficient way of powering the board because of the voltage drop across the diode. And you're definitely right about that. There are more efficient ways to do this sort of power selection or power mux if you wanted efficiency for both power inputs. But for us, we only care about the efficiency on this power input, on the 12 volts, because that's what's going to be used in the actual car during races. This is just going to be used for testing and programming the boards. So just using a simple diode is perfectly fine for us. So there you go. There is the power layout of one of our circuit boards. So I'm going to go ahead, finish this off by placing a line around our circuit here and place some text. Change it to be a font of 24 and call this power. There you go. And I'm going to change this to be red. Perfect. Okay, now as promised, we're going to go ahead and focus on the layout. Now, before we create our PCB document, I'm going to discuss a little bit about how we want to route everything up. Now, so the most important thing is going to be the high frequency loop. So that high frequency loop is essentially going to consist of this capacitor down to ground, all the way along here to this capacitor, to our magnetic inductor element, back through the IC and back through this capacitor. So we're looking to keep this loop here as tight and as small as possible. And that's going to help with the characteristics of the power supply, it's going to help with EMI, the EMI or the electromagnetic interference produced by the buck converter, as well as a number of other things. These sort of control circuitry add-ons don't really matter as much as far as routing goes. So we're going to focus on this loop here and keeping it as small as possible. That's really the main consideration that we have to make. Okay, so I'm going to go ahead and create a PCB document, add new to project, PCB. All right, now I'm going to go ahead and make this a 4-layer PCB by going to design, Layer Stack Manager. It's going to open up the Layer Stack Manager. And I'm going to go to Tools, Presets, change this to 4 layers. I'm going to go ahead and delete this layer, which is also going to delete dielectric number 4. And then change these 2 layers to signal layers, even though we are mostly going to be using them for planes. It's a little easier when you go to your manufacturing if they're all signal layers. Go ahead and close that, save it, and then close it. And that's going to have, now we have our 4-layer PCB. Nothing really looks much different, but I am going to change some of the properties. So go to Panels, Properties, and I'm just going to go ahead and change it to millimeters, and then I'm going to change the grid size by just pressing G. Or is it Shift G or Control G? Okay, I forgot what it was, so we'll do it in properties. Or I'm gonna be honest, and I forgot how to change the grid. There we go. Should just be to hit G, and I'm gonna start with a grid of 0.25 millimeters or quarter millimeter. It looks like my project's pane went away, so I'm gonna bring that back by going to View, Panels, Projects. I'm gonna rename PCB1 to be I think that this sort of tutorial series is going to become a redo of the front VCU. So I'm going to call it front VCU. We'll call it 0.3. Okay. So to sort of import those all of the stuff on our schematics, we go to Design, Import Changes from Schematic, Validate Changes, make sure everything's green, Execute Changes, should all still be green. Go ahead and hit Close. That's going to bring in all of our good parts. Now, before I start rooting everything out, I want to discuss, if you've never used Altium, about PCB design rules. So in Altium, your rules are properties about your PCB design that Altium automatically checks for you. So these are things like clearance between parts, clearance between these pads, clearance between traces between pads, all kinds of things like that. Now, where do you get these rules from? Are they just arbitrarily defined? No, you usually want to get them from your manufacturer. That's going to be making your PCB to make sure that you're designing printed circuit boards that they can actually manufacture. Now, you can go to individually set rules by going to Design, Rules, and individually setting all of these rules. Now, I'm going to do something different. I have already exported all of the rules from another project, and I'm going to be importing those rules into this project. So I can do that, import rules. I'm going to select all of them, hit OK, and I'm going to go ahead and see if I can find where I had those rules. So I believe they were in let's see. Okay, we're going to go ahead and export them from somewhere instead. Okay, so let's go to front VCU. Go to its PCB design. I'm going to go to Design, Rules, right click and Export Rules. Select all of the rules. Oh, cancel. Export rules. All the rules, okay. I'm going to call it that. Okay, go ahead and hit save. Now I'm going to go back to the project that we were working on. Go to, oh, wrong one. Design, rules, right click, import rules. Oh, I'm hitting control accidentally. Hit OK. We're going to navigate to where I had that other board saved. And open up our rules. Click yes. Click OK. And now we have all of our rules imported. And so yeah, you can see here is our buck converter IC. That's going to be the start of where we're laying everything out. Okay, so we have our IC here. I'm going to go ahead and hide our label for now. Cool. And we're going to start laying out our components. So like I said, we need to start with this sort of loop that we're looking at. So we have our inductor, our capacitor 1, and our capacitor 2. Okay, so you have our inductor. I'm going to go ahead and move and rotate this component 180 degrees by hitting spacebar twice. And I'm going to go ahead and rotate this to be, we'll put it like this. And like I said, this is going to be sort of an iterative process. Okay, so now we have C1, C2. That's going to make up our most important loop. Okay, so C1 goes here. Like I said, we'll get rid of this again. C2, C2 will go here. So let's go ahead and flip that around. Okay. We'll move this, we'll route this a little bit farther. Place that over there, that over there. Now, this so far looks like a pretty tight loop to me. Obviously, it can always be slightly tighter, but you know, this isn't a incredibly high-speed application, so you know, we don't want to go crazy with this. We want to make sure it's manufacturable. Now we have R2. Let's see, where do we place R2? And like I said, that's where the trouble of this begins. Is, you know, this component here has to access these two pins. You know, so how do you edit your prime loop configuration to include these excess components? Again, we'll get rid of this this sort of component label. And okay, so as you can see, this can get a little bit messy, right? So obviously we would like to have this loop, right, as closely tied as we can get it, but that would require putting these components on the outside of the loop, which would require a lot of extra work running the paths sort of under. So we have to kind of alter our perfect loop and go for one that's really just satisfactory. Hmm. Okay, so I like this. If you go to your 3D view, you can see that this should be plenty manufacturable. All of these components will likely be soldered on for us, or actually not really, but some of them will be. So I'm going to start running traces. So here's our power PG pin. Like I said, this is not going to be carrying a lot of current. So this can be just a normal trace. So I'm going to hit Control W and run this trace from here to here. Right now it's set to 0.2 millimeters, or I'm sorry, it's set to 0.381 millimeters trace. I'm going to go ahead and edit that to be 0.254 millimeters. And that will get connected just fine. I'm going to, and this is a constantly evolving process, I'm going to make the decision to reverse this, and I'll explain that later. You might say, oh, Sam, that 3.3 volts is farther away now. We'll take care of that in a moment. So I'm going to route that directly. Again, power reset, that's just one of our control pins, so it doesn't really matter too much. Now we have our power configuration. We will take care of ground in one moment. Okay, so, and here is power V in. And for this, I'm going to use something called a polygon port, just because power V in is going to be one of our areas that's going to be carrying a lot of current. So I'm going to go and place polygon pour. And I'm going to start here. Come over here. 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 Right. And I'm going to go ahead and assign this to be a power V in, re-pour it, and there you go. Now you have your polygon pour. There's a few sort of knickknacks to consider here. This does not like how close the polygon pour is to this trace, and so it won't really pour the whole thing. So I am going to change the bottom of this, and it's not letting me have the flexibility I want. So I'm going to go ahead and change the grid settings down to 0.1. Oops. And I'm trying to report that. Still not exactly what I want. But I think that's good enough. So there's our power V in polygon pour. And now we have our power switch output here. Yep. Okay. So we have our power switch output. I'm going to go ahead and create another polygon pour. Down around here. Okay, go ahead and give that the net label power underscore switch and record that. Amazing. Okay, so we are getting close. So here is sort of where our loop is forming. It's kind of forming around our buck converter here. The one thing I don't like about where we're going with the layout right now is having this power good pin be so close to our inductor here. Although power good is an output, and so I'm not as concerned about it. If one of these two guys were as close to this inductor, I would be more concerned than about this layout. And like I said, you can sort of learn more about some of these minor considerations in the videos that I will post in the description. Okay, so now let's focus on our 3.3 volts plane that we've got going on over here. Okay, this 3.3 volts pin does not really matter because this is our V-sense pin, and that we are going to have to route it up, but it doesn't really have to be part of our big power plane here. And so we are going to discuss that one later. So we're going to place polygon pour. We're going to create our plane. Around here. Call it plus 3 V3 and report. Okay, it looks a little bit awkward around here. I'm gonna see if I can make that look any better. Aesthetics are always important in PCB designs, but they are definitely not the most important thing. So I think we will leave it for now. Okay, our 3.3 volts plane, and now we're going to create a ground plane here. Okay, let's go ahead and place polygon pour. Create this as a ground and report it. Beautiful. Okay. Now we have ground. ground 3.3 volts. Okay, perfect. So now what I'm going to do is place a via here, and I'm going to, that is a large via. Place via. I'm going to go ahead and edit its size by clicking on it and going down here to make the diameter is going to be 0.5 with the hole size being 0.3 millimeters. Okay, there's our new via. And I'm going to place it under the IC, and it has to be quite well centered, otherwise it's going to give us an error. And I'm going to assign it a net label 3.3 volts. Beautiful. Connect it up there. Change the width of our trace there to be 0.2 so that it doesn't cause any clearance issues. That sort of green overlay means the clearance issues. And then we have our ground pin here. And this is going to be a pretty important ground pin that will be carrying a lot of current. So what we're going to do is place lots of vias. Those are way large, so I'm going to copy and paste these. I'm going to place lots of vias right around here. 1, 2, 3, 4. 1, 2, 3, 4. If we can get away with it. Nope. Okay. Okay, 4 vias. I'm going to make them all ground, and I'm going to place them as a polygon pour, or I'm going to create. That is definitely going to cause some clearance issues. They will deal with that in a moment. And I'm going to assign this to be ground and report. So yeah, we have lots of clearance issues over here. Let's go ahead, see if we can fix any of that. Our grid is again quite large and not giving me the control that I really want. But that should be about fine for that. Still a slight issue over here, so we'll give that more clearance. Report. I'm going to go ahead and change the grid one more time down to this and just report that a little bit. Report. That's okay. Okay, that is exactly what I was looking for. So let's go ahead and we'll change the grid right back here. Okay, this is the sort of rough component placement that I am looking for. We have our loop goes from here, through our inductor, across this capacitor, and across this capacitor. So there's our loop. Now we have these ground vias and this 3.3 volts via sort of running to nowhere. and we're going to go ahead and look. We're going to create the planes that we need. So we have our ground plane here on the second layer, and obviously this is going to be much larger. This is going to be the size of the PCB. But we're going to create a polygon pour. Like I said, it's going to become much larger, about the size of the PCB when we are working on it. I'm just trying to make this line straight. And I'm going to call this, I'm going to give it the ground net. And I'm going to come back here. Or I'm going to go ahead and copy that. Go to power. And it's not working. I'm going to place a similarly sized polygon pour on the power layer. And call this plus 3V3 volts. Okay, get rid of these two guys for now. And we will go back to the top layer. I'm going to repour this, Then I am going to go ahead and hide, and let's go ahead and look at our top layer. Okay. I made two small mistakes. We need to place some vias. Let's go ahead and copy and paste them. We'll just do a few for now. I'm going to go ahead and shelve this, and I will show you why in a moment by right-clicking, going to polygon actions, and going to shelve selected. That way we can sort of see where our capacitors are and see where we can place these vias without them causing any clearance issues. And this grid is annoying me, so I think I'm just going to permanently leave it at 0.1. Okay, and let's bring this polygon back by going to Tools, or I'm sorry, Design, Tools, Polygon Pours, Restore One Shelved Polygon, and I'm going to go ahead and repour that. I made the mistake of not making these ground vias. And now I'm going to go to Tools, Polygon Pours, Repour All. And now you can see there is no longer a missing connection between this ground and this ground because it is connected across that ground layer that we just created. I'm going to move this. Tools, Polygon Pours, Repour All. Amazing. Okay, same thing for 3.3 volts. Let's shelve this. Shelve selected. And let's go ahead and place a bunch of vias. 1, 2, and I'm doing so many in order to increase the sort of current carrying capacity. And we're going to make these all 3V, 3V, as this is probably way excessive. But why not? So design, or I'm sorry, tools, polygon pores, restore one shelf polygon, and tools, polygon pores, repore all. And there we go. Now we have our Q1, which was our reverse polarity protection. Just going right here. Okay. Q1 and our D1. Okay. So that looks good to me. As does that. I'm going to go ahead and expand our polygon pore to include the p-channel FET, and I'm going to do that with another polygon pore. I should just go in and edit the other one, but I'm kind of lazy. Power V in. It might not like this. Before. Interesting. I'm not sure it's why it's creating this little odd shape at the end. I don't like that. Interesting. Let's go ahead and get rid of this. And we're just going to go ahead and edit the shape of this. I think I'm just going to delete this polygon pore and remake it. Sorry for the delay. It is late at night. Like I said, we can go back and make sort of some fine adjustments to this pore once it is complete. Power underscore V in, repore it. That looks good. That looks good. That looks great. Change that a little bit. See what we can do there. And there. For of course, it does not like that. Repore. That is acceptable to me. Okay, there's our power in pore. Now we have our big ground pore over here. Let's take a look at this in 3D. Looks good so far. Okay. Place some vias. Okay, let's copy and paste them again. I'm just going to do 3 or 4 of them. Make them all ground net labels. And place a polygon 4 surrounding the grouping. I'm going to have to edit that a little bit and make this ground. Report it. Go to Tools, Polygon Forest, import all, and that's going to fix that error there. Amazing. Oh man, if I have to remake this one again. Core. Make it power in report. Okay, that's fine. Power in, ground, 12 volts in. We will handle in a moment. But yeah, that is all for our power section routing there. This is what it looks like in 3D. But yeah, I hope this was educational. Like I said, there's going to be some extra videos about buck converter routing in the description of the video.